Your smartphone feels like it was built in the future. It can translate languages, find a face in a crowd of photos, and answer questions in seconds. But deep inside, the main thinking pattern it uses is not new at all. The surprise is that your phone still runs on ideas that were already taking shape in the 1800s, and it still hits a limit that engineers have been fighting since the 1940s. That sounds like a joke, so let's make it real. When you open an app, your phone does something very old school. It reads instructions from memory, pulls data from memory, and then crunches that data in a separate place, over and over. If the instructions and data arrive late, the crunching parts sit idle, waiting. That waiting, more than raw speed, is one of the biggest reasons computers feel stuck. Here's the promise of this video. By the end, you'll see your phone differently. You'll see why faster chips didn't magically solve everything. You'll see why artificial intelligence makes the problem louder, and you'll see the strange new ideas, some almost sci-fi, that try to break out of this trap. In 1854, mathematician George Boole showed how logical statements like true and false could follow strict rules, like math. That Boolean logic is the reason computers love the simple pair 0 and 1. Every modern chip still builds bigger thoughts from tiny yes or no switches. Then, in the late 1800s, Herman Hollerith used punched cards, paper with holes, as a way to store information and feed it into a machine for counting and sorting. His system helped process the 1890 US Census, and it helped launch the punched card industry that later grew into IBM. It's the same big idea we still use today. Store information in a form a machine can read, then process it at scale. Even earlier, in the 1800s, Charles Babbage designed the analytical engine, a mechanical computer concept with a store for memory and a mill for calculating. It was never finished, but the blueprint is weirdly familiar. Memory over here, computation over there, and a program telling the machine what to do. So when we say your smartphone is a 19th century device, we're not saying it's literally built with gears and punch cards. We're saying its deepest habits, binary logic, stored information, step-by-step instructions, come from that era. The glass is new, the habits are old. Jump to the 1940s. Early electronic computers could be painfully hard to reprogram. One famous machine, ENIAC, often required rewiring and patching to change tasks. A new idea changed everything. Store the program itself in memory, right next to the data, so the machine can quickly load instructions the same way it loads numbers. A key document describing this stored program design is John von Neumann's first draft of a report on the EDVAC, circulated in 1945. Historians also note that credit for the stored program concept was disputed because the EDVAC work involved a larger team, including engineers J. Presper Eckert and John Mauchly. Still, the basic design described in that era became the default pattern for general-purpose computing. Here's the rulebook in simple words. The computer has a processor. Think of it as a chef, and it has memory. Think of it as a pantry. The chef can cook fast, but only if ingredients arrive on time. The chef keeps doing a loop: fetch an instruction, fetch the data, do the work, store the result, repeat. This looks so normal today that we forget it's a choice. It's not how thinking must work. It's just a very successful design that made computers flexible. A stored program machine can run a calculator one moment and a video game the next, simply by loading different instructions. Now comes the twist. This design has a built-in traffic jam. If the processor and memory are separate, something has to carry instructions and data between them. That link can become the narrow neck of the bottle. When the processor can compute faster than it can be fed, the whole system slows down. On October 17, 1977, computer scientist John Backus gave a famous lecture and used the phrase von Neumann bottleneck to describe a choke point in the way we program and think about computation. The phrase stuck because it also names a real hardware problem. Too much information must squeeze through a limited path between memory and the processor. By the 1990s, researchers described a memory wall. the growing gap between how fast processors improve and how fast memory systems can deliver data. The result is simple. For many tasks, waiting for data becomes the true cost, not the math itself. And here's where your phone enters the story. Phones feel slow not only when the processor is weak, but when apps must pull lots of data, photos, maps, messages, and machine learning models from memory and storage. Every scroll and every smart feature becomes a tug-of-war between compute and data movement. For decades, a kind of miracle made this problem easier to ignore. Transistors got smaller, and engineers packed more of them onto chips. On December 23, 1947, Bell Labs researchers demonstrated the first working point-contact transistor, and later the transistor effect earned a Nobel Prize in physics in 1956. Then the integrated circuit arrived. On September 12, 1958, Jack Kilby successfully tested an early integrated circuit at Texas Instruments, and Robert Noyce is also widely credited as a key inventor of the integrated circuit. Putting many components onto a single piece of semiconductor material made modern electronics possible. In 1965, Gordon Moore observed that the number of components on integrated circuits was rising quickly, a trend now called Moore's Law. For a long time, you could buy a new device every few years and feel a real speed jump, even if software stayed the same. Then another bonus helped. In 1974, Robert Dennard and colleagues described scaling rules that, in simplified terms, suggested smaller transistors could also be more energy efficient when voltage scaled too. For a long stretch, performance improved without power exploding. That era didn't last forever, but it shaped what we expect from technology. Around the mid-2000s, the free lunch started to end. Power and heat limits made it harder to keep raising clock speeds, so chip makers leaned harder into parallelism, multiple cores, and specialized accelerators. Major reports described this shift as the end of dramatic growth in single processor performance and a move toward parallel computing.
But notice what did not change. Even with more cores, the phone still needs to fetch instructions and data, move them, and store results. More cooks still need ingredients. The bottleneck doesn't vanish, it just moves around. Modern chips use a whole bag of tricks to make the old design feel new. The biggest trick is the cache, tiny, ultra-fast memory placed close to the processor, like a little countertop pantry. If the data you need is already there, the processor keeps moving. Chips also try to predict the future. They guess which instructions and data you'll need soon, then fetch them early. When they guess right, everything feels smooth. When they guess wrong, you get those little stutters because the chip must wait for reality to catch up. Phones also lean on specialization. They use dedicated hardware for graphics, video, and machine learning. Blocks that can do certain tasks with less energy than a general-purpose core. This is one way the industry keeps progress moving without rewriting the entire rulebook overnight. Still, these are mostly workarounds. They're brilliant, but they don't fix the core problem. Data still has to move, and moving data costs time and energy. Artificial intelligence is not just more math. Modern AI often means huge amounts of data moving through layers and layers of computation. That makes the von Neumann bottleneck louder, because AI often needs to move huge tables of numbers, weights, and lots of temporary results, back and forth again and again. This is also an energy story. Researchers have shown that moving bits around a system can be surprisingly expensive compared to doing simple arithmetic. In other words, your phone's battery is fighting traffic, not just thinking. That's why reducing data movement has become a guiding rule in modern chip design. Major reports on computing performance keep repeating the same lesson. Memory farther away costs more to reach, and reducing movement is often the fastest path to better efficiency. So the phone's most futuristic features, voice assistance, photo magic, and translation, push hardest on its oldest weakness. That's the irony. The more smart we make software, the more we slam into the old separation between memory and compute. If the wall is memory over here and computed over there, then one escape plan is obvious: put them closer together. or merge them. That idea shows up in many forms, including processing in memory, near-memory compute, and compute in memory. Different names, same goal: less travel. In 2022, researchers described a compute-in-memory chip using resistive memory, aiming to store AI weights and compute inside the memory itself. This kind of approach tries to turn memory into a warehouse into a factory. Another escape plan is brain-inspired hardware, called neuromorphic computing. The core idea is to design systems where memory and computation are more intertwined, closer to how networks of neurons work. It won't replace your phone tomorrow, but it's a real research path being explored. And there are hybrid futures too. We may keep the von Neumann style for general tasks, but offload specific problems to new kinds of chips, including analog AI hardware that computes where the data is stored. Some labs are exploring these ideas with devices such as phase change memory to reduce data movement. Here's the clean answer. Your smartphone is modern in materials, scale, and polish, but it is still powered by an old blueprint. Boolean logic from the 1800s still sits at the foundation. Stored program computing from the 1940s still shapes the main flow, and the separation of memory and compute still creates a bottleneck we can't fully optimize away. That doesn't mean progress stopped, it means progress changed. We moved from faster clocks for everyone to a world of smarter architectures, parallel cores, caches, and specialized engines. We're squeezing more life out of the same core idea, the way airplanes got better long before anyone built a rocket. And the next big jump may not feel like a faster phone at first. It may feel like longer battery life, cooler devices, and AI that runs locally without burning through energy. If that happens, it'll likely be because we finally reduced the miles the data must travel inside the machine. So the title isn't an insult to your phone, it's a reminder. The future doesn't arrive all at once. Sometimes it arrives as a new screen wrapped around an old, stubborn idea. And the real revolution will be the day our computers stop spending so much time just moving information from one place to another.